Hey all, happy Friday. Um, so today we're going to go over the test from chapter 11 that I didn't walk you guys through last time, just kind of walked you through the conceptual background for the test. We're just going to do a couple of examples today, just to get you used to the math. I want to show you how similar it is to the chapter 9 test that I taught you a couple of videos ago. Um, but first want to give you just a quick refresher on when we use this test. So in chapter 11, the test that we're covering is called the dependent sample t-test. It is a within subject statistical design. Okay. In other words, you're taking one group of individuals and testing them at either two time points or under two different conditions. So I'm going to give you a few different examples of um, specific examples of tests where you would adopt this design, just so you guys can start thinking about how you might actually use this in a research setting. One of the things that you should be considering when thinking about this design is there likely to be a lot of between subject difference in whatever variable it is that I'm studying? If you're studying something that's really subjective, right, where there's likely to be a lot of variability from person to person, well, then you might want to use a within subject design, because then every individual serves as their own control, which means any difference in performance or whatever your dependent variable is due, hopefully, solely to your independent variable. Okay, so that's the idea there. So a lot of the examples that I'm going to read you, and we're probably going to do two or three today, just to like really get you guys understanding it. One of the things you will notice through all of these examples is that what the authors are studying is likely to vary a lot person to person. There's a lot of subjective reporting, subjective self-report. Humans vary a great deal from person to person when they're asked questions about rating attractiveness, for example. That's one of the questions. So we'll do a couple of them. I'm going to start with the one that's in my PowerPoint. So if you go to slide, I'm going to be skipping some slides, but bear in mind that the slides that are in there are kind of very how-to at this point. How to write your hypotheses, how to subtract when you're finding your difference scores for these tests. So we're going to be on slide 34 essentially. So we're going to have data from a few mice, and we're going to look at some things there. Now, one other thing real quickly before we really get into that is, again, I want you guys to start building out a mental flow chart of when to use these tests. So right now you have two tests fully under your belt. Forget chi-squared for a second because it's a little bit of an oddball one. You have the single sample z-test and the single sample t-test. Now, before I say anything else, I'm going to give you a quick second, or you can pause the video, to tell me mentally what the difference between those two tests are. When do we use one and not the other? Okay, remember, we use the single sample z-test when we have a sample mean, drawn directly from sample data or not, doesn't matter, that we wish to compare to a population mean, which is known, and a known population standard deviation. If we don't have those things, particularly the population standard deviation, we have to use a single sample t-test to accomplish the same goal. It's kind of the same concept. One sample of data, in this case it's usually raw data, a sample mean is created from that sample. You compare that sample mean to something. It can be a comparison mean, or it can be a population mean, or just some point of reference. The example that I gave you in my chapter 9 video was, the Surgeon General recommends that you guys sleep 7 hours per night. I have a sample of students about your age. I want to know if they sleep roughly 7 hours per night on average. That kind of thing. That's not a mean, but it is a number that's worth comparing something to. So it doesn't have to be a mean to do this. And then the key thing about this chapter 9 test, the single sample t-test, is that your population standard deviation is unknown. It has to be inferred from your sample, which means you have to calculate it. So a quick and dirty rule of thumb, normally I wouldn't break it down for you guys in this Mickey Mouse way, but if the problem gives you a standard deviation, it's more than likely a z-test. If the problem gives you a set of raw data, a single sample, it's more likely to be the t-test. Okay, because it wants you to calculate a sample mean. It wants you to calculate sums of squares and variance and standard deviation and so on. Okay. And then, okay, so that covers the two designs that we would have if we had a single sample. The next layer of our flowchart is going to be, okay, well, what happens when we have two groups or two levels to our independent variable that we want to compare? Okay, so the question you're going to ask yourself to separate the two tests that you're going to learn is are my data within subject or between subject? Another way of saying that is, are they dependent or independent? The first one that we're going to learn is for dependent samples. And the reason we do it is because it's when you actually sit down and do the math, you're going to be like, oh, that kind of looks like the single sample t-test. So the math transitions really well, which is why we're skipping chapter 10 for the time being. So that's how it works. Now, if your sample two separate groups of individuals, completely different humans, and it's not a matched pair design, we'll get to that later, then you have an independent sample t-test. So far it's single sample z, single sample t, dependent sample t, and then independent sample t, which is what we'll do next week. Probably take us the whole week to kind of work through that. So we're going to work through some examples. I'm going to do them on the whiteboard behind me. I tried to do a screen share sort of situation, and it was actually really good, but the problem is I can't narrate over it, in which case you're literally just watching me put numbers into Excel, and I can't imagine that's going to be very helpful for you guys. It might be more helpful for SPSS because you guys are mostly completely unfamiliar with it, but watching me put numbers into a spreadsheet is not going to be that helpful. So I'm going to suck it up and just do it on the board, and hopefully I have enough board space for the next couple of tests, and I'll just keep erasing if I have to. So we're going to do the one that's on slide 34. I'm going to be looking at the data, so if it looks like I'm not looking at the camera, forgive me. So the way I set this up, first I'm going to read this to you guys. And for the time being, I'm going to skip the hypotheses for this, just because I kind of want to show you how the math works, and then we'll talk about the hypotheses that you're actually using and what the test is actually doing. All right, so I'm interested in the change of ambulation, movements basically, produced after a single dose of cocaine in rodents. To test this, I collect data from 5 mice. I record their number of ambulations before and after a single dose of cocaine, and I obtain the following data. So what I have is I have 5 animals. If I'm doing this like a proper experimental design, what I should do is at my baseline, I should give them an injection of saline to serve as a control. I have it listed here as before cocaine. That's totally fine too. I mean, it could be saline versus cocaine or before cocaine and after cocaine, however you want to imagine it. And I'm going to give them that injection, and then I'm going to put them in this box. Now, just because I know many of you guys probably aren't used to studies like this that look at locomotor activity, I'll explain to you how this works. It's actually really simple. If you ever want to study hyperactivity in rodents, the easiest way to do it is to get a box. You can get a really, really fancy high-tech one that has a laser beam grid projected over the bottom of the floor, and if the animal moves around a lot, it breaks a lot of beams, and there's a little counter on the side that says this is how many beams they broke. And obviously animals that are more hyperactive are going to move more, and they're going to have higher LMA scores as given by that counter. Another way of doing it is you could take a very simple plexiglass cage with no bells and whistles, record the video, and then lay a piece of clear gridded paper over your computer screen and just score them manually. You can do it that way. So it's a very, very common approach for studying this. I just want you guys to sort of understand how this would work. But this is another one of those perfect examples where using a within subject design isn't a bad idea, because it's possible that there's a pretty high degree of variability from animal to animal in terms of how sensitive they are to cocaine. That's not going to be as variable as other variables that we might talk about in this class, like some of the ones we're going to use in the book, but it's a good example of when it might be okay to use the within subject design. So the first thing I'm going to do is I'm going to take that data and I'm going to write it on the board behind me. For reasons of subtraction, I'm going to write the after condition first, and you guys will see why in a second. Okay, so this is going to be, it says after cocaine, before cocaine, but I'm actually going to do cocaine saline. Just going to redesign this study a little bit. Okay. So all of the animals were given saline first and then given cocaine. If you give them cocaine first, then you have to worry about a washout period, and there's unlikely to be any effect of saline. So at least in this case, normally that's not how you would do it, but at least in this case, that's how we're gonna run it. So I'm gonna write down my cocaine data. So it's 60, 55, 40, 30, and 55. Don't be worried about the big numbers here. You'll see that they're going to change in just a sec. And then 30, 25, 40. All right, awesome. Now, let me just minimize this so hopefully you guys can see. Nope, my head was in the way the entire time. That's okay though. Now you can see. So there you go. There's our raw data. Now, remember, this is another name for this test is the paired sample t-test. Okay, what does that mean, paired sample? Well, it means that these two numbers are paired with each other. Not because it's a matched pair design, though you can do it that way, because these come from the same animal. This was animal 1 with cocaine and without cocaine. So if we want to know what the animal's difference due to cocaine treatment is here, all we have to do is subtract. That's it. It's pretty simple. Subtract from left to right, and that's going to produce a column of difference scores. Not the same difference scores you use when you calculate sums of squares, but they are difference scores. Difference between time point A and time point B. So maybe this will shock you a little bit, but when we actually go to do this test by hand, you're not going to be using this raw data for much other than subtraction. You actually have to think about this. Extract your data from the differences between these two time points. And then from there, I'll show you how this works. So I'm going to subtract from left to right. The reason I put the cocaine group first is because I want to retain my correct direction of difference. If I did saline minus cocaine, I would get negative 15, and that would suggest that an animal treated with cocaine moves or produces 15 fewer beam breaks or ambulations. That's not correct. So I'm doing it this way. Now, technically, if you arrange your columns correctly, what that would really mean is you have 15 fewer for saline rather than 15 more for cocaine. But I like my T statistic to reflect the actual difference, so I'm going to do it this way. Again, if you do this the other way and subtract the other way, the results of your test will be the same if you're doing a two-tailed test. We're going to treat this like a two-tailed test, so it really doesn't make that much of a difference. So, okay, so subtracting. So from left to right. So 60 minus 45 is 15. 55 minus 45 is 10. 40 minus 30 is 10. 30 minus 25 is 5. And 55 minus 40 is 15. So there you go. Now, that is our raw data. That column is what we're actually interested in. That's what's going to lead us to producing a T statistic that we can use to make a claim about these hypotheses that we have, right? From here on out, this test is identical to the single sample t-test. So if you can do that test, you can do this test, which is why I kind of have them for your next quiz, for example. It'll be a chapter 9/11 quiz because the tests are so similar. There's a couple of minor notable exceptions, and you'll understand why. So think about what we're actually going to do. We're going to run a t-test on this set of data with a comparison mean in mind. And our null hypothesis always states that there's no difference between what it is we're looking at. What number could I compare these two to suggest no difference or no change? You guessed it, 0. So basically what I'm going to do is take a sample mean from this, compare it to 0, extract my standard error of the mean from this. That's the part that you guys don't like because it takes forever. And then that's it. My test is done. Look up a critical value, call it a day. So let's do that. Obviously, we're looking at a mean here that's going to be pretty big relative to the 0 that we're going to be comparing it to, but we don't know if it's going to be significant or not, so we still have to do the math. So let's try. First, sample mean. So that's 15, 10 is 25, 35, 40, 55. 55 over 5 is 11. So our mean sub D is 11. Now, why do I use M sub D? It's the mean difference score. You could just put M, that's fine. It's however you want to organize your thoughts, but if you're ever looking at my notes and you see M sub D, just that's what I'm getting at. Now, this is the part that sometimes confuses students. This is a step that they skip. All you've done thus far is calculate your sample mean. A lot of students think, oh, I have my difference scores, let me square them. No, 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 no. You don't have your difference scores yet. You have your difference scores from level 1 of your 2 variables versus level 2. You don't have your difference scores that reflect your actual data and its difference from the mean. You still have to find those as normal. So we're going to take this 11 and we're going to subtract it out from each one of these numbers like we normally would. So I call these my d sub d scores, difference of the difference, if you want to call them that. So make sure you guys can see. I'm going to pull this a little closer. Okay. So you subtract out 11 from these. I'll draw it out for you guys just so you guys can see. Normally I don't do this. And then you're going to get 4, positive 4, negative 1, negative 1, negative 6, and positive 4. Okay, so those are my difference scores. We're doing sums of squares, right? So what's the next step? We square these. So that's d sub d squared. Okay. So that's 16, 1, 1, 36, and 16, 18, 34, wow, my brain. 70? Yeah, 70. Okay, so my sums of squares is 70. Whew, hard part's over. We have our sums of squares. Remember, that's always the hardest part of anything, is calculating that. Now we have to calculate our variance and standard deviation, our standard error of the mean, and then our t-statistic. So I'm going to erase the raw data here. You can rewind it back if you need to see it for any reason. It's a nice thing about doing this via video. Just so I can set up my equation for variance and standard deviation. So remember, variance, or SD squared, for a sample is given by your sums of squares divided by n minus 1. So in that case, this is 70 divided by 5 minus 1. So 70 divided by 4, that's 17.5. Let me get my calculator. Normally I would trust myself much more, but if I make a mistake in my video, it's very hard to undo. So 70 divided by 4. Yeah, 17.5. Instinct was correct. Okay, so 17.5 is my variance. Now, my standard deviation is merely the square root of that. So let me do square root 17.5. Where'd it go? 4.18. Hopefully that's what you guys are getting at home. Okay, so remember, so SD squared, take the square root of that, you get SD, and that's standard deviation. So 4.18. And then lastly, next step is standard error of the mean. And remember, we write that as SD sub m, or SEM, however you want to do it. 4.18, that's our standard deviation, over the square root of n. So that's 4.18 divided by square root of 5. Not going to be the prettiest number ever, but we can still calculate it. So let's see. You guys hopefully have a calculator in front of you. So that's 2.24. Okay, so it's 4.18. I'm getting 1.87-ish. SD sub m equals 1.87. All of that, now I have all of the ingredients for my t-test, right? And I actually can do the equation right down here, so hopefully you guys can see it. So remember, we're looking for our t obtained here. Our formula is going to look like this. It's m sub d minus 0, just get all that out of there, over our standard error of the mean, right? It's in the notes if you can't see that. I know it's a little bit small. So with the numbers that we actually have, substituting those in, we've got 11 is our mean sub D, 0 is still 0, over 1.87. So we're going to get a number that's going to be slightly larger than 5. I'll get that number for you in just a second. .89. So our T obtained here is 5.89. So the question we always need to be asking ourselves at this juncture, okay, I have an obtained T statistic. Is it big enough for me to say that there's a difference between these two things that I'm actually trying to study? In other words, can I reject my null hypothesis? I know we didn't write out the null hypothesis yet, but this is our first crack at it, so we're just looking at the math. Okay, so let's see. We got to look up a critical value. So go to our t-table. So hopefully from chapter 9 that rings a bell. That's going to be on page 575, right? Degrees of freedom. Then subject t-test, or the paired sample t-test. Still n minus 1. So I have 5 individuals, 4. Okay, my degrees of freedom is 4. My proportion in two tails combined, because I'm doing a two-tail test at 0.05, that's what it says on the slide. My cutoff would be 2.776. Okay, so if I was going to check myself here, I know this is small, guys, sorry. There's negative 2.776. There's positive 2.776. Those are my rejection regions, the black bits. Does my obtained T statistic fall into those rejection regions? Well, if this is 2.776, then 5.89 is all the way out here. So yes, and I'd be rejecting my null hypothesis. Null hypothesis in this case would obviously state that there's no difference in terms of ambulations between animals that were treated with saline versus animals that were treated with cocaine. And that's it. It's that simple, right? I just want you guys to understand the logic of what's actually going on here. The most important part of this test from a standpoint of your understanding is that you know what's going on when we find the original difference scores, okay, when we subtract between our two levels. Because all we're doing is producing a difference between those two levels. Think about it. What we're saying is that difference between those two levels, in this case the difference between cocaine and saline, is due to nothing more than whatever our independent variable is, right? I'm going to give you another example so that you guys can kind of see it in a different light. This was the example that I was going to give you guys last time. I tend to not like it that much because it's a little bit sexist, if I'm being honest. It is the sort of, this research gets done. There's nothing sexist about the research per se, though it makes certain assumptions that I don't like. But nonetheless, the numbers are simple, so it should pan out to an easy thing to run. And it's not a really big, there's not a lot of individuals in this sample. So, okay, I'm going to read it to you. It's number 17 on page 337. And if you want to do this for yourself, even before I do it, you can do it. Check yourself. Answers in the back of the book because it's an odd-numbered problem. I'm going to put the answer behind me in just a sec. I'm going to erase the board real fast, too. I'm also going to try and write down my hypotheses as we go because I didn't do that for the last example. So once I have everything read out loud, I'll write the hypotheses first, and then I'm sadly going to have to erase them because I need the board space to actually do the problem, which stinks, but it's whatever. Okay, so 17. Research indicates that the color red increases men's attraction to women. That's from Elliott and Niesta 2008. It's a real study. In the original study, men were shown women's photographs presented on either a white or a red background. Photographs presented on red were rated significantly more attractive than the same photographs mounted on white. In a similar study, a researcher prepares a set of 30 women's photographs with 15 of them mounted on a white background and 15 mounted on red. One picture is identified as the test photograph and appears twice in the set, so that each individual gets to see it on both backgrounds. That's why they did it that way. Once on white and once on red. Each male participant looks through the entire set of photographs and rates the attractiveness of each woman on a 10-point scale. You see why I think this is a little bit, not 2020. The following table summarizes the ratings of the test photographs for a sample of the n equals 9 men, so our sample size is 9 here. Are the ratings for the test photograph significantly different when it is presented on a red background compared to a white background? Use a two-tailed test with an alpha of 0.01. So we'll keep that in mind for this one. Okay. So the first thing we want to do is write out all of our data. I'm actually going to write our hypotheses first too. So a couple of different ways you can word this. I like to state that the mean difference between attractiveness ratings between red and white backgrounds is equal to 0. Okay, and then for your alternative, it would be all of that, but not equal to 0. Fair enough, right? So you can say it that way. You can also, some of you guys might be more comfortable with saying there's no difference between attractiveness ratings on red backgrounds and white backgrounds. That's a much more, I think, concise way of saying it. The reason I'm phrasing it this way is I kind of want you guys to understand how the test is working. Technically, both statements really mean the same thing, but what we're actually doing is looking to see if the mean difference between red and white is equal to 0 or not equal to 0. That's the same as saying that, red equals white or red minus white equals 0. It's the same mathematical kind of idea. So mine's a little bit more long-winded, but if you understand why I did it that way, then you really grasp the nettle of how this test works. So that's how you would write it out. I know that's a lot to keep in your mind, but maybe jot it down because I'm going to have to erase it to actually do the math part. So we're going to do that. Nice single-digit numbers for this one, so it shouldn't be that bad. So in this case, I'm just going to do white then red. Okay, so that's 4, 6, 5, 5, 6, 4, 3, 8, 6. 9 individuals though, so we're going to be doing a little bit more math. 7, 7, 8, 7, 7, 8, 9, 9, 7, 9, 9. Okay, there we go. So that's our raw data. Just get it a little closer to make sure you guys can see all the math that I do. Okay, so just like last time, first step is to subtract. Now, I wrote these white then red, but I can subtract in any direction I want as long as I'm consistent. So just from eyeballing this, that may not be the best idea to do it that way. You could just, again, as long as you're consistent and refer to the direction of the t statistic, knowing how you subtracted, you're fine. So they hypothesize that red will, their research hypothesis, forget their statistical hypotheses, their research hypothesis is that the red backgrounds will be producing higher attractiveness ratings. So I'm going to just subtract this way. You normally wouldn't do it that way. If you do 4 minus 7, you get negative 3. If you do 7 minus 4, you get positive 3. All that's going to affect is the direction of your t. It will not affect the magnitude. And if you're doing a two-tailed test, it won't affect your significance either. So I'm going to do red minus white. So if you see these numbers working opposite, that's why. Okay, so I'm going to extract my difference scores now. So 7 minus 4 is 3. 7 minus 6 is 1. 8 minus 5 is 3. 9 minus 5 is 4. 9 minus 6 is 3. 7 minus 4 is 3. 9 minus 3 is 6. 9 minus 8 is 1. And 9 minus 6 is 3. So look at that. Across the board, every guy in this sample rated the pictures as more attractive when they're on red versus white. Now, was it significant? Let's find out. It's okay to have mixed positives and negatives in your difference scores if some individuals fell on the other side of the coin. So for example, if two of these gentlemen rated it more attractive on white, then you would get a negative number in this column. Totally fine. It's going to affect your mean, but it's totally fine. That's in fair play. I don't want you to think that all of these have to have the same sign. They don't. So let's find our mean real fast. So we're going to be dividing by 9. 3 plus 1 is 4, 7, 11, 14, 17, 23, 24, 27. Perfect. 27 divided by 9 is 3. So our mean difference equals 3. Still whole numbers, still nice and easy. Next step, now we're going to be finding sums of squares. So we're going to take our difference scores, but this time, difference scores from our sample mean relative to our raw data. So we're going to subtract out this mean difference from all of these scores. We can actually ignore this data for now. It's done. Once we have the difference scores, we don't need it. Okay. So subtracting out 3. I'm not going to be writing it down, but you know what I'm doing. 0, negative 2, 0, 1, 0, 0, 3, negative 2, and 0. And then squaring that. Let's do some D. 0, 4, 0, 1, 0, 0, 9, 4, 0. Okay. So you add those up and we get the sums of squares. 5, 14, 18. Right? 13, 14, 18. Awesome. Okay. You guys heard my wife just run into the room and out to distract me. Okay, so we have our sums of squares. So next step, obviously, is going to be to find variance, then standard deviation, standard error of the mean. We can do that. We have room right here, so let's do that. Okay, so our variance is going to be 18 divided by 9 minus 1. Remember, it's for a sample, so it's n minus 1. 18 divided by 8 is going to be 2.25, I believe. Just double checking myself again. I don't have you guys to yell at me when I do my mental math wrong. Yeah, 2.25. Okay. And then our square root of 2.25 bear with me. 1.5. I should have known that. 225 is a perfect square. That's a fun fact. 1.5. All things considered, that's a pretty nice standard deviation. Standard error of the mean is 1.5 divided by the square root of 9. Oh, that one's easy. Okay, so square root of 9, so the square root of n, right? 1.5 divided by 3 equals 0.5. So our standard error of the mean is 0.5. So there we go. We have all of the ingredients necessary to do the t-test, right? So we can do our t obtained right down here. It's our mean difference, 3, minus our, basically our null hypothesis mean, which is 0, with the idea that there is no difference between these two things, over 0.5. 3 minus 0 is 3, over 0.5 is 6. Wow, it's a sizable t-statistic, even bigger than the last example. Now, remember, we're using 0.01 as our alpha, just because it's stipulated by the problem, just to kind of flex our muscles in terms of how we look up our t-critical values. Let's turn to page 575 and do that. Now, the only difference is here, so first we have to figure out what our degrees of freedom is, 8, right? Because we have 9 individuals in our sample, so our degrees of freedom is n minus 1 in this case, so that's 8. So we're going to go into the df8, and then we're going to scroll across. Now, our proportion in two tails combined is not going to be 0.05 for this, it's going to be 0.01. Why? Because that's our alpha. Okay, so let's scroll across. 0.01 is going to be 3. I think it's very hard to line it up the way I'm looking at it. 3.355. We'll call it 3.4. Not really going to matter because that's gigantic. Right? So there we go. Right? So we've got a two-tailed test, so that's negative 3.4, positive 3.4, not 34, 3.4. Okay. Where's 6? Well, 6 is all the way over here. Reject the null. And what do we state? State it in plain English. Yeah, it turns out that men rate women's photographs as more attractive when they're on a red background versus a white background. Now, you might be asking yourself, and this is a really good question if you are asking yourself this, Drew, you're doing a two-tailed test, but you just said more attractive. So just because you do a two-tailed test doesn't mean you can't talk about the direction of difference if your t-statistic suggests a direction of difference, as it often will. Looking at how we subtracted, because I subtracted, even though I wrote this way, I subtracted that way. Having a positive t-statistic given by a positive sample mean suggests that the red column was higher than the white column. Okay, now that means that they're more. This provides whether it was significant or not, and it was. So there you go. You can say more on the red than on the white as a virtue of that. You don't have to rely on a one-tailed test to use that kind of verbiage. I don't want you guys to think that you are. Now, when you're talking about it statistically, in terms of the hypothesis you write out, yeah, totally fine. When your null hypothesis is still going to state that there is no difference between the two things and that your alternative is a difference, and you would state that's correct, but you can actually elaborate on that if, in fact, you have the data to do so. Okay, so you don't need to rely on a one-tailed test to make directional claims. Only when you absolutely have no interest in the other tail of the distribution should you be adopting a one-tailed test in this case. So that's another great example for you. I'm going to give you guys one to work on by yourselves. If you want to send the answer to me and run it by me, go for it. I'll read it to you guys. And then I want to say a little bit, just a couple more words on adopting the within subject design in general, because this is going to be another good example of when you would want to do it. So remember, just Monday morning quarterbacking this test, why do you think they use the within subject design? I'm going to ask you that rhetorically. Think about it for a second, then I'm going to tell you. Why do you think they would use a within subject design for a test like this? Why use the same people twice? Why not have two separate groups of individuals? These people see white, these people see red. Because when you're gauging attractiveness ratings, there's a lot of subjectivity. A lot of this is going to be variable, unique to the individual, right? So when you get the opportunity to serve as your own control, any difference between the two levels, white versus red, should be, at least theoretically, due to the independent variable and not any other third variable or something you couldn't control for. It's not always the case. There is always some random variability. Time can have an effect. Position within the sequence that the picture was shown could have an effect, right? Would it have a significant effect? Well, we don't know. We could test that. There's other, admittedly, more advanced statistical approaches that could test that sort of thing. But for the most part, the idea there is that you are the same person at time point A and time point B, and any difference between those two time points or in those two conditions is due to your independent variable. Okay. So that's it for today. Practice with some of the problems from chapter 11, and I'll post this for you guys. We'll do some chapter 10 stuff